Thank you so much for the introduction, Keith, and for the invitation to come speak with you all today. I've really enjoyed the conference so far, and I'm excited for today's talks. So hello, my name is Emily. I am a fifth-year grad student at Ohio State. And today I'm going to be talking about the abundance ratio trends in the Milky Way disk and bulge. And like many of the talks that we've heard over the course of this conference, I'll be talking about how we can use 12 plus abundances in these surveys with thousands and thousands of stars to learn about our galactic enrichment history and chemical history. The work that I'm going to be talking about today has been done in collaboration with Jennifer Johnson, David Weinberg, James Johnson, Fiorenzo Vincenzo, and many collaborators in APOGEE and GALAH. So I'll start with the Tinsley-Wallerstein diagram, which we've seen many times throughout this conference. And as you all know, we have the high alpha and the low alpha populations in this diagram. The high alpha stars, however, are kind of misnamed. They're not actually high in alpha, they're low in iron. And as we move along the high alpha track, the abundances decrease in magnesium to iron because we have increased iron contribution from type 1a supernovae. So in this talk, I won't refer to these populations as high alpha and low alpha, but rather as low 1a and high 1a respectively, to better describe their enrichment history, because the stars that are high in alpha abundances are actually high in alpha abundances because they have lower contribution from type 1a supernovae. These two populations are distinct, so it's important that we study them separately and we look at their abundances as populations and don't mix them together. The other thing that I will be doing differently from many other abundance works is looking at abundances in magnesium space rather than in iron space. Iron, as we know, is produced by core collapse supernovae and type 1a supernovae, while magnesium is almost a pure core collapse element. So when we look at elements relative to magnesium, it's easier to separate out this core collapse and type 1a contribution. So this was done in Weinberg et al. 2019, where they really looked at how we can use magnesium as a reference element and what we can understand from looking at abundances in this space. And so this is an example of one of the Hayden-like diagrams from their paper, looking at magnesium on manganese. And so we have different bins of increasing radius to the right and increasing height as we move up in this plot. The blue stars are the high 1a stars and the red are the low 1a. And the solid lines in each panel are the same, and those represent the median abundance trends for the entire disk's high 1a and low 1a populations. Within each individual cell, there's the black points, which are the medians for only the low 1a and high 1a stars that are in those bins. And you'll see that in every panel, the black points overlap with these solid lines, meaning that the median high 1a and low 1a trends are the same throughout the location in the disk. And this is really important information and can tell us about the consistency of these nucleosynthetic processes throughout our disk. So what can we learn from these sequences? Like I said, we can learn about the enrichment sources. And we can do that through looking at the locations of these sequences and their separation or their inclination. So if we have some element X that has a high 1a and a low 1a sequence that are very close together with small separation, we can infer that that element is dominantly produced by core collapse supernovae. This is the case for oxygen. So in the panel on the right, I'm showing oxygen abundances for 80,000 stars in GALAH, and we see that the high 1a and the low 1a sequences are right on top of each other. And oxygen is also produced almost entirely in core collapse supernovae. As we increase the sequence separation, that suggests that an element has more contribution from type 1a supernovae. So we see this for iron, which is about 50% from core collapse and 50% from type 1a at solar metallicity. We see a significant separation between the high 1a and the low 1a sequences. And then finally, we can have some inclination in these sequences, which tells us if the core collapse or type 1a contribution to that element has metallicity dependence. And so manganese is a great example of this. It has strong metallicity dependence, and that's seen through the steep slope in the high 1a and the low 1a trends. But we can do better than just qualitative descriptions of the sequence separation and inclination. We can quantify these separations and use those to infer the core collapse and type 1a contribution to the different elements. And so this is done through the two-process model, which was constructed in the Weinberg 2019 paper. This model assumes that all stars have contributions from core collapse supernovae and from type 1a supernovae, and that there's two processes that we could describe as vectors, and that every star or bin of stars has some amplitude of each of those core collapse and type 1a vectors. The model has a few assumptions, that magnesium is a pure core collapse element, that magnesium core collapse, iron core collapse, and iron type 1a supernovae yields are independent of metallicity, and that the low 1a magnesium on iron plateau represents pure core collapse enrichment. So anything off of that is suggesting increased type 1a contribution. And we can fit these processes to each element and determine a ratio of the type 1a to core collapse contribution. So the process to understand these abundances is to fit the core collapse and type 1a processes to our median trends, and then to use those to derive the relative contribution from core collapse supernovae and type 1a supernovae to element X. So at this point, we would say, like, okay, from the median trends, we can infer that oxygen is 100% core collapse, nickel is 40% core collapse, and so on. We can use this then to extract only the core collapse component of our observed abundances. So we no longer have the mix of core collapse and type 1a contribution. And in order to understand these abundances in the entire field, we can compare our empirical core collapse supernovae yields to theoretical core collapse supernovae yields. And so that is what I'm showing in this figure. It's a comparison of our empirical and theoretical yields, where the empirical yields are derived from GALAH abundances through the two-process method that I described earlier. And the theoretical yields are coming from the core collapse models of Supbold et al. 2016. And so in this plot, the y-axis is showing the difference in the core collapse abundance between the model and the observational yields. So if the values are above 0, our theoretical abundances are over-predicting some element X relative to what we would infer from the observational constraints. And if it's less than 0, then the model is under-predicting relative to our observational constraints. The different points represent different core collapse supernovae explosion landscapes. So the dark blue is where every star from 8 to 120 solar masses explodes. And the colors approaching yellow are less explosive. You'll notice that no model reproduces the results exactly. There's no point color that is exactly at our 0, line. So this can tell us a little bit about our observed abundances and maybe suggest that there's problems with our reduction pipeline, but it also can tell us about our theoretical abundances and help us to understand places that we need to improve our core collapse supernovae yields. We could do this with type 1a as well, but it's a little harder. And so we've just done this with core collapse supernovae yields for now. And if you're interested, you can read more about it in my paper from earlier this year. This is for solar metallicity disk stars. But from looking back at our plot from Weinberg et al. 2019, we know that if we picked any point in the disk, we would get the same results because our sequence separation is consistent throughout the disk. So at solar metallicity, we would find the same core collapse to type 1a contribution. For example, the manganese here, it has large sequence separation. So it has a significant type 1a contribution, and that type 1a contribution is happening everywhere in the disk. The Weinberg paper has only looked at the apogee disk, like I said, and they only go to an inner radius of 3 kiloparsecs. So a question that I have asked is what's happening in the inner galaxy? Is this consistency staying the same as we approach the bulge? And going into this project, we didn't know what the answer was going to be, right? We had a couple of predictions. It could either be the same as we'd seen for the disk. That might be because the same kinds of stars are enriching the ISM. Core collapse and type 1a processes are contributing in the same ratio as they are in the disk. But it also might be different. The bulge is unique. It hosts our bar and our bulge, and it might have a different enrichment history or a different IMF or a different black hole landscape for core collapse supernovae. It might have additional enrichment sources. So there's reasons that it could be different than it was in the disk. So in order to look at this, first I'll just go over that there are prior comparisons between the bulge and the disk. The literature on the subject doesn't come to any strong conclusions about what elements agree or disagree between the bulge and the disk. It is also hard because most of the prior works have had fewer numbers of stars. They're usually in the hundreds. But with APOGEE DR16, we're able to do this with a much larger sample of stars. DR16 expands APOGEE to the southern hemisphere, so it has great access to the inner galaxy. And we can use the APOGEE abundances to compare the high 1A and low 1A median trends in the Milky Way's disk and the bulge to try to understand differences in the nucleosynthetic or star formation history of our different galactic locations. So we select bulge stars using APOGEE DR16 data. We take everything with a radius less than 3 kiloparsecs and a height less than 5 kiloparsecs. We apply a variety of quality cuts, and we end up with a population of about 11,000 stars in the bulge. Their location on our magnesium to iron versus iron to hydrogen plot is shown on the left. And you can see that just as we see in the disk, there's a bimodal population. This is something that was seen in a lot of the work with DR16 and hadn't been seen previously because of insufficient data. But with all of the abundances in DR16, it's very clear that the bulge exhibits this bimodal population and has two distinct populations, the low 1A stars and the high 1A stars, even though the high 1A population is much less extended than we see in the disk. We'll compare the sample of stars to a sample from the bulge that is matched in log G distribution because we found that there were systematic abundance correlations with log G. And in order to remove those, we needed to match the log G distribution of our samples. So here are the bulge abundance distributions for these 11,000 stars in APOGEE. The high 1A stars are in orange and the low 1A are in purple. The medians for the high 1A and the low 1A sequences are overplotted as the larger points. And you'll see that there are many elements that we know come from core collapse supernovae that have the sequences very close together, which is promising. So oxygen, we have very close, and aluminum, they're very tight. So this again suggests that these elements are dominantly produced in core collapse supernovae. And then we also have our elements that have larger sequence separation, like nickel and manganese, suggesting that they have a higher type 1A contribution. We can then compare these median trends to the median trends of our disk. So again, the bulge high 1A is in orange, low 1A is in purple, and the disk population medians are the gray points that are plotted underneath. And for almost every element, you can see that the median trends are basically overlapping, which is awesome and suggests that we could extend the conclusions from the Weinberg paper to the inner galaxy. There are a couple of interesting elements where this is not the case. So sodium, manganese, and cobalt, we see differences specifically in the high 1A sequence. For all three of these, it looks like there's some level of offset between the bulge and the disk, and like the bulge has a steeper high 1A sequence than the disk does. These differences, though, are still only on the scale of about 0.1 dex or less, so they're very small. And it's hard to understand if this is coming from differences in the IMF or the enrichment history between the bulge and the disk, or if it's still coming from systematics. And it's harder to interpret because these are some elements that have high systematics and APOGEE, and they're not the elements that we trust the most. So it will be interesting to see how this progresses as we get more data and better quality data in the future. So I'll wrap up the first part of my talk with the conclusions from this bulge project. First, just saying that we can infer the relative core collapse and type 1A contributions to a given element based on their large population trends in our X on MG versus MG on H space, and that using magnesium space is really helpful for understanding the contribution from core collapse supernovae and type 1A supernovae to a given element. We saw that the bulge and the disk trends were very similar for almost all of the elements in APOGEE, which suggests that the nucleosynthetic processes are fractionally contributing. The the same throughout the galactic disk and the inner galaxy, and that it's independent of galactic location. For the last 5 minutes or so of my talk, I'm going to talk about something different, which is what about the individual stars? So everything that I've discussed before has been based off of the median trends of the high 1A and low 1A populations. But there's also a lot of really interesting detail in the stars that don't lie on the median trends and that have different abundances. So what can we learn from those stars as well? To understand this, I'm going to go back to the two-process model that I talked about before. Again, this model assumes that all stars have contributions from core collapse supernovae and type 1A supernovae. This model fits a process parameter, which are the Q's in this equation, and these are calculated from the median high 1A and low 1A sequences. There's a process parameter for each abundance for the entire population. We then have process amplitudes, which are determined for each star, and they give us the amplitude of the core collapse or type 1A process for a given star. This is fit to a weighted fit of 6 different elements. We use magnesium, iron, calcium, silicon, and nickel. And from this, we could predict the abundances of any element that is in GALAH or APOGEE based on the fit to the median sequences and the amplitudes to these 6 elements. So this is telling us about the core collapse and type 1A contribution to a given star based on the population values. And we can use this to predict the abundances and compare the predicted abundances to the abundances we actually observe. So I'll stick with my manganese example and show you some quick plots for this. So this is for a sample of unflagged GALAH stars with log G between 3.5 and 4.5. The distribution on the left is the observed manganese on magnesium abundances, and in the middle is what we predict. You can see that overall, they look very, very similar. We've definitely captured the large trends of the population, but on a specific individual star level, there are differences between the observed and the predicted distributions. And so on the right, I'm showing a histogram of the differences between the observed and the predicted abundances. Most of them lie close to 0, but there are tails that extend out beyond 0.2 dex in either direction. We can look at this for individual stars as well. So in these plots, I'm showing the exon H abundance for all of the abundances we look at in GALAH. The observed values are in black. The predicted values are in the open circles. The first and the third are stars that we would say are pretty well fit by our model. We ignore the neutron capture elements though. And then the second and the fourth are stars that are not very well fit by this model. And so in the second, you can see that this star has a much higher potassium value than we would predict. And in the fourth, this star has a much lower manganese value than we would predict. These are really interesting deviations and could help us to identify stars that are chemically interesting and don't have the mixture that we would assume from core collapse or type 1A contribution to those elements. It is a little difficult though, because we don't know what all we can trust. So some of the predicted abundances that deviate from, some of the observed abundances that deviate from our predictions do look real. So here is one star that has a high sodium and a high copper value relative to what we would predict. And if we look at the GALAH spectra, so I'm showing now the sodium and the copper windows, the black points are the observed values, and then the purple line is the observed spectra that is reported by GALAH. If we create a spectra for our predicted abundances and compare it, that is shown in the orange line. And so in both the sodium and the copper cases, it's pretty clear that the predicted spectra is not well fit to the spectrum, and it's much better fit by the observed that GALAH reports.
2 minutes.
So, thank you. There are, however, problematics in the spectra, and so some of the stars that have high deviations between our observed and predicted values are actually just flagging stars that should have been flagged by GALAH. So this is an example of one that has lower oxygen than we would predict and lower potassium than we would predict, along with a bunch of other deviations that you can see in the top plot. But when we look at the oxygen windows, it's pretty clear that this star is the spectroscopic binary. And when we look at the potassium, it looks like there's been problems with the telluric subtraction in this window. So even though this star was not flagged as a binary or had problematic potassium, going through this algorithm and finding that the star is not well predicted by our two-process model can help us to identify that, okay, maybe we should not trust either the oxygen or the potassium, and maybe some of the other abundances from this star as well. So I will end with the conclusions from a little bit of the first part and the second part of this talk. But the main one is that the median abundance trends are really powerful tools to help us understand the origin of the elements and the enrichment history of our galaxy. And that while the two-process model can describe a lot about our galactic population's abundances, there are still really important residuals. And it's very interesting to look at the deviations from the two-process model to try to find interesting stars that might have awesome enhancements or depletions in elements and have cool enrichment histories. So with that, I will end and take questions. Thank you.
Awesome. Thank you very much. I'm going to clap as well and do my virtual clap. So we have a couple of questions already, raised hands and in the chat. And I also have a question, but Danny Horta asks, great talk, Emily, exciting results. Quick question. Could the fact that you get different sodium abundance or sodium for profiles for bulge to disk be due to contributions from disrupted globular clusters in the inner galaxy or due to the metal multiple populations phenomenon, I guess?
It could, but we are looking at the bulge. So we have a sample of 11,000 stars. And we did, if you look at the paper, do a quick little investigation into whether some of these stars could have come from accreted origins or not. And there is some stars in this like accreted space of chemical abundances that we've heard about in many of the talks from a couple days ago. And my concern there is that there's not a ton of stars in that space. And so when we're looking at these median trends, they are pretty unchanged by the inclusion or exclusion of those stars. And we see these differences at a range of metallicities in these diagrams as well. So it's more evidence that there might be something happening with a larger population or a larger systematic than just individual smaller populations that could be causing this problem. Or interesting result.
Great. Rosie asks a similar question to me, so I'm going to go ahead and comment on it. Do the chemically anomalous stars have unusual kinematics? And I'm going to broaden that question one step further, which is if you look at your process amplitudes, do they correlate at all with kinematics or orbital dynamics?
So that is, I don't know the answer to that right now. We're still like ongoing in this investigation. I don't think that the process amplitudes correlate with kinematic information on a larger scale. We've been looking a lot at the different correlations between the deviations in our abundances and in the process amplitudes that we derive. And right now, it doesn't look like there's correlations with the kinematics. I have not checked for the like chemically interesting stars if they have interesting dynamical information, but that would be really interesting to follow up on. Thank you.
Great. Sven?
Yeah, thanks. Great talk, Emily. I was wondering, so for the stars, how fast can you predict all of, like, if you would apply this for all of GALAH, how fast can you predict like weird signatures that then again the GALAH team could use to look into when we do the next data release, for example? Yeah, so I have been doing a lot of looking at spectra by eye, as you know. And so I've been looking based off the chi-square value that we assign based on the fit. So how well we predict the spectra, and it has a higher chi-square value if there's high deviations. And looking at stars that are in the 99th percentile of this chi-square distribution, so stars that are really not well predicted by our two-process model. I looked at a sample of about 100 of them, and like from my quick looking at the lines, I estimated that about 4
had trustworthy abundances for all of the lines that deviated by more than 4 times their error. There were a bunch, like I think maybe 25 that I could identify as binaries, 25 that had some level of omission. So the ones that are in the 99th percentile probably are almost all problematic spectra. Lower than that, I'm not sure, and it might be harder to distinguish between the chemically interesting and the systematic errors. Yeah.
Yeah, cool. Thank you.